Hi, Saket, can you hear me?
Hi Arjit, would you like to share your screen?
Okay. So let me do that. Okay. So you can hear me, right? Clearly?
Yes, I can hear you.
Okay, good. Okay. So let me share the screen. Okay. Can everyone, Saket, can you see the screen?
Yeah, I can see. Yeah, I can see the screen now. Yes.
Okay,
Yes.
good.
Yes.
Okay,
I
so,
can see the screen. Corset is written 8/1/21.
yeah,
Got well?
yeah, yes.
Okay. Let me.
Today is 8th, right? Okay, yeah, okay,
Yeah.
yeah, good.
Let
So I
me
start?
just 1 second. Arjit.
Sure. No problem.
Okay, so we already 2:32. So, yeah, so let me introduce Arjit. So he is currently faculty at Indian Institute of Statistics, Calcutta, and his area of interest are computational geometry, then streaming algorithm, and he's one of the pioneer in computational geometry in the country. And today he will talk about corsets in 2 1-hour lectures. So this is one lecture, and then there will be a lecture followed by this at 4 o'clock. So Arjit, off to you.
Yeah, thanks for the extremely flattering introduction. So, one small correction, Saket, and I don't think it is your fault. The name of the institute is Indian Statistical Institute. Not
Oh,
Yeah, but it should be Indian Institute of Statistics. If you,
okay,
okay,
okay.
so yeah, no problem. So thanks for inviting me. So both Saket, Fahad, and Venkatesh. So yeah, so good. So I will be talking about. I checked the program, and it sounds like the main concentration was on understanding the streaming algorithms and like communication complexity, proving lower bounds. So I will break my talk into two parts. So part A, I will be looking at what is called like Corset in streaming. Okay, applications of or like framework of Corsets in streaming. Okay, framework of Corsets in streaming. And in part two, so what I will be doing is I will give like the classical thing where it came from. So Corsets in CG, computational geometry. Okay, good. So let's begin. What is the framework that we are working on? So we are getting points P1, P2, Pi, Pn over a stream, and we want to compute some functions on it, right? I mean, that is the basic idea. And it may be frequency estimates, it may be different things. Okay, so the focus in today's first talk and the second talk also is you want to compute the points that you are getting, the data that you are getting over a stream are geometric points, and you want to compute some uh, interesting property of those points. Okay, so let's look at like the thing. So let's say these points are, you will be getting points from RD. Okay, uh, and so let's look at the most classical thing that you can think of. So suppose in the offline mode, so let's say I give you n points in RD. What is the natural thing you want to compute? One natural thing you may want to compute is okay, what is the smallest enclosing radius of the smallest enclosing ball for these points? Okay, so let's say this be the points at capital P. So for these points, so what is the radius, or what is the smallest enclosing ball? Smallest enclosing ball. So we denote it as MEB for P. Okay, it's a very natural question. Okay, So it may the problem may look like extremely like a simple one that we could have like looked into in our school days, but this has like large applications. Okay, so the generalization of this is used a lot in clustering. Okay, so okay, but we are looking at the simplest case. So what do you want to do? Given a set of points, I want to compute the smallest enclosing ball. There. So let me declare the offline problem, offline variant, how to solve this in the next class. But now the point set P that we are getting is one at a time. We will be getting the points from P over a stream, and I want to compute the smallest enclosing ball. Okay. Okay. So and one of the goals of the streaming algorithms for geometric problems is you want to store as few as points as possible and still want to, you may not able to exactly compute the smallest enclosing ball, but you should be able to compute the approximately the smallest enclosing ball. Okay, so what do I mean by that? Okay, so let me say what are the goals. Okay, goals is first is want to store as few points as possible, points of P as possible to compute. So here when we say compute, always think we are doing streaming. So always when compute means approximate the smallest enclosing ball of P. Okay. This is the thing what we want to do. Okay. You may want to do something even stronger. Okay. Okay. Here what we define what is called a, here the concept comes of cost functions. Cost functions associated with a point set. Okay, so let me explain what this idea is. So let's say so you have a set of points P in subset of RD. Okay, you can associate a cost function CP parameterized by the point set P that will be giving you values for points in RD to R. Okay. Okay. So the basic idea is so for let's say for the smallest enclosing ball, I want to do the following for a given point set. So for MEB, the cost function is the following. Okay, CP of X is max over all Y belonging to P, Y minus X. Okay. So here when I write 2 means it's like Euclidean distance. Okay. Is this function clear? So by the way, if you have questions, please stop me and like ask questions. Okay. So for a given point set, I want to associate a cost function. Okay. One interesting thing that we may be interested in doing is the following. So for let's look again in terms of MEB. I want to store a set Q, which is a subset of P, as of size as small as possible, such that the following happens. Okay, C. So let me write it. Okay, CP of X is less than equal to alpha times, let's say, C Q of X greater than equal to. Okay. So not only am I preserving distance smallest enclosing ball, but I will be preserving distance of any point in RD to the point set P. So rather than calculating the distance of any point RD to the point set P, I will be computing it with the point set Q, which is a subset of P. And still, I will get a good approximation factor. This alpha will be the approximation factor. Okay. So this is a slightly harder thing, right? I mean, it may be that your set of points that you can select from P is such that the smallest enclosing ball for that is the smallest enclosing ball is approximating. It can be approximated by looking at the small set of points. But here I'm asking for something even more. I'm saying not only am I will preserve distances in RD from any point in RD to the point set. I will calculate that distance, which is basically CPX. Okay, and I will be calculating the distance to CQX. Okay, CQX will be a good approximation of CPX. Okay, by the way, this side of the equation is trivial for us because Q is a subset of P and the function is defined in such a way that this side follows trivially, but the other side is something that is of interest. Okay, and this will be called alpha corset. Okay, so more formally, what you have is the following. So let's say you have a cost function C, which will be parameterized by the point set. Okay, and you want your corset to satisfy some properties. Okay, so let me write the definition formally now. Okay, so definition. Okay, so for alpha greater than 1 and the cost function C, we say a subset of P is a alpha corset of P with respect to C, the cost function, if for all T subset of RD, we have the following. For all X in RD. So this is what is called, so let me write it. This is called alpha corset. Okay, so the definition that I wrote here is even stronger than what I mentioned just before. Okay, what does this definition say? It is saying that so for every point set P, you have an associate cost function CP. Okay, you want a subset. The previous definition, what we were saying, we want a subset of, we want to select a subset of P, say let's say S. Okay, and want the size to be as small as possible, such that this equation was satisfied without the T. Right? This was the basic thing we said. Here, what we are saying is not only should it be satisfied for P, but it should be satisfied for all extensions of P. Right? T can be an arbitrary extension of P. For that also it should be satisfied. So S union T for any T will be a good approximation, will give you good approximation for the cost function C for CP union T. Okay, is the idea clear? The extension idea? Okay, so why is this definition like given? So this definition was basically like tailor-made for looking at problems in streaming. Okay, in streaming we don't really know, okay, what point set we will be seeing in the future. We have seen some set of points now, and let's say we have seen a small amount of point set. For that I have computed some good approximation, but I want that good approximation should be usable for the future point set that I will be seeing. Okay, the future point set that I will be seeing is basically taken care by this definition, that for any T, this equation should be satisfied. Let's call this equation 1, let's say. Okay, so one of the thing that we will be proving is in the first class is we will be showing that. So let me write Corset, the cost function, let me write it like this. For minimum enclosing ball, C of MEB, okay, has a 1 plus epsilon corset of size order So let me write order suffix D. Okay. So okay. So D means here the constant depends on D. Okay. But in terms of its behavior with respect to epsilon, it is epsilon to the power D minus 1 by 2, or square root epsilon to the power D minus 1. Okay. For any set of points, okay, there will exist a coset of size square root epsilon to the power D minus 1. Okay. And a constant that depends on D. Okay. Which is nice, right? It says that the size of the coset is independent of the size of the point set P. Okay, so this is one of the important results that we will be seeing. Proof is not hard, but this is what we will be seeing. Okay, so again, like so let's say again, as I said, this definition of coset is more like tailor-made to handle problems in streaming. Okay, so there are some nice properties this definition satisfies. Okay, so let me give you some of these properties. Okay, so nice properties. So nice properties of corsets. Okay, the first one is what is called the merge property of corset. Okay, so what is this property? It is if S is an alpha corset of P and S prime is a beta corset of P prime, then S union S prime will be a alpha beta corset for P union P prime. Okay, so again, this is a nice thing. So let's say I have partitioned my set of points into number of sets. For each of them, I have calculated a coset. Okay, then I can combine the coset to still get a coset that satisfies some properties. Okay, so still satisfies. It may not be as good approximation individually, but still some approximation guarantee will still be preserved if I take union of corsets. Okay. Okay, so this so let's see. I will do proof of one of them, but let me give another property that we will be using is what is called reduced property. Okay, so if S is an alpha coset of P and S prime is a beta coset for S, then S prime will be a alpha beta coset for P. Okay, so this is what is called the reduced property, and this is another one. The top one is called merge property. Okay, so again, as you can see, the reduced property also makes complete sense. Okay, I mean, in terms of streaming. Okay, so let's say I've looked at some set of points, I have built a core set. Okay, that let's say whose size depends on the set of points. So for minimum enclosing ball, it is independent of the number of points, but for all core set it may not be the case, right? For some function you need probably size of n will come into the picture. Okay, so you have building a core set for a particular set of points. Now you have seen even more points. Okay, so their core set is growing, so you cannot still preserve the, so and you have some limitation on the number of points you can store. Okay, then what this result is saying is if you are willing to give away the approximation guarantee a bit, okay, then you can get a smaller size core set for the core set that you currently have, and you can still, that new core set will still have some guarantees left for the original set of points. Okay, is this too Property is clear? I
Sir,
hope. Yeah, sure.
hello.
Yes.
Sir, my first intuition was that it should be a alpha plus beta corset, but then I saw alpha beta corset, so I was thinking that
Yeah. So
yeah,
it's not alpha plus beta. It will be alpha beta. So let me give you the proof. These are like two very simple. So let me, as a
yeah,
like a warm up exercise. Let's see proof of both of them. Okay, it's a very simple proof. Okay, so let's see it. Okay, as with any lectures, you should always give the simplest proof. Okay, so that you don't get into trouble with students. So let's try to prove the first one. Okay. So in the first one, what we are saying, okay, I have a S is an alpha coset for P, S prime is an beta coset for P prime, and then we want to prove S union S prime will be an alpha beta coset for P union P prime, right? Okay, so just by definition, okay, so let the cost function be C. So let the cost function be C. Okay, so now what do you want to show? So let me write it out. So S union S prime union T. So let T be an arbitrary extension. Let T arbitrary extension. Okay. So we know this is less than equal to P union S prime union T of X. Why is this? Why can I write this? I can write this because S is a alpha coset for P. Okay, so this equation I can write. Okay, similarly I can write this P union Q union T of X. This I can write. What is Q? P prime. Sorry. Okay. This is because now S prime is a beta coset for P prime. Okay. So then again I will write. I will use the fact now that S is an alpha coset for P. So it will this I can write. And now I want to use the fact that S prime is a beta coset for P prime. So we get. Okay. So the equations that we want, the terms that are already there. I want this term should be less than equal to this term, and that should be less than equal to this term. Okay, is it okay? This proof?
yes, sir, yeah.
Okay, yeah. So just playing with the definitions and nothing fancy happening. Okay. So what about the other one? Other one is also just going through it. Okay, so let me. You just start with this again. S prime is a beta coset for S. So we can write C S union T of X. Okay. S is an alpha coset for P. So I can write this is less than equal to C of P union T of X. Now I want to use the fact that again S is an alpha coset so of P. So alpha C S union T of X, which is again less than equal to S prime is a beta coset for S. So alpha beta. Okay, just like again the terms of interest are this one should be less than equal to this term, and which should be less than equal to this term. Okay, is it okay how the proofs are going? Okay, if you have a question you can ask. Okay, so these are like these are nice properties that are like kind of the definition of Corset is basically set up so that we can like have these nice properties. Okay, these are not surprising. Okay, this is happening because the definition is particularly set up like that. Okay, so that it has like applications in streaming. Okay, so now let's look at another property which does not follow from the definition of corsets. Okay, but which will be extremely useful for our designing corsets. Okay, not all corsets satisfies this definition, but this is a very useful one if to have in terms of building corsets. Okay, and we will see and why that is the case now. Okay, so first let me give you the definition. This definition 2 is what is called disjoint union property. Okay, so what is a disjoint union property? Okay, so by the way, I'm not writing the cost function C again and again. Okay, whenever I write corset, you should always have in your mind like there is a cost function at the background on which we are working. Huh? Okay, so let's say S be a alpha corset for P. Okay, and then let first and the second thing assume that S prime be a alpha corset for P prime. Okay, so we will say the cost function has disjoint union property if S union S prime has a disjointness property if okay, so let me write. Okay, so let P, let me write the definition at the beginning once again. So let P and P prime be disjoint sets, and we have these two corsets with it. Okay, so we will say the cost function C has a disjointness property if S union S prime will be a alpha corset for P union P prime. Okay, so this disjointness property is stronger than merge property. Okay, right? Merge was saying combine, then the approximation factor decayed by at most the product. Okay, here it is saying if they're disjoint, then the approximation factor will be preserved. Right? If the approximation was alpha for S1 S prime and alpha for S, then S union S prime will still be an alpha corset for P union P prime. Okay, this property does not follow from the definition of corsets. Okay, particular cost function satisfies this. So as you can see, like you can guess easily that as an exercise I'm giving you, show that take home. This is like just from definition it will follow. Show that the cost function for minimum enclosing ball satisfies definition 2. Okay, so this is not yeah. Come on.
Yeah, I have a question. May I?
Yes, always.
So this holds only when both these approximation ratio is same, like alpha and alpha. It doesn't hold for
Yeah.
alpha.
So let's say it is alpha and beta. Okay, then the approximation ratio that will be preserved is max of alpha comma beta. Yeah. Right. So I mean, so if it is an alpha corset for P, then it will also be a beta corset for P if beta is bigger than alpha. Right.
Okay. Okay.
Right.
Yeah.
Yeah. So the cost function I'm assuming takes non-negative values. Here I'm assuming cost function is taking non-negative values. Yeah. Okay. Good. So as a take-home thing, so just work out that cost function for the minimum enclosing ball doesn't like satisfies this disjointness property, which is nice. Okay, good. So let's see why this disjointness property will be useful for us. Okay, I mean, if you're designing, so as I said, like all these definitions are there just to like for particularly for applications in streaming, right? I mean, so let's see whether this, just looking at these definitions, can we get some interesting results in streaming. Okay, so let's say first prove this theorem. Okay, this is for the consequence of disjointness property. Okay, this is basically of disjointness property. Okay, so let epsilon be greater than 0. Okay, if C has a 1 plus epsilon corset of size A epsilon, and C satisfies disjointness property, we write it like dp, let's say. Okay, then for then we can maintain a 1 plus epsilon corset over a data stream of size order. So it should be A epsilon by log n times log n, where n denotes the number of points we will see. We will see over the stream. Okay, so is the theorem clear? So what's the idea? So let's say you have a cost function, okay, which satisfies the disjointness property. Okay, and let's say it has a if I wanted 1 plus epsilon corset for this cost function, okay, I can get it of there exists corsets of size A epsilon, let's say. Okay, then if I get data like points over a stream, okay, one after the other, okay, I will be able to maintain a 1 plus epsilon corset over the data stream. Okay, but the corset will be of size at most A of epsilon by log n times log n. Okay, is the statement of the theorem clear? See, A epsilon is the size of the corset that you can maintain. Okay, but there is a one problem with that is that corset you may be able to compute only after you see all the points. In streaming, I cannot store all the points to compute that corset. Okay, so that is why the corset that I can maintain over a stream will be worse in terms of size than the corset that I can maintain when I know all the points in the offline model. Okay, so that's why there is like, it will get worse. So the size of the corset that I need to maintain will be bigger when I'm maintaining over a data stream. Okay, but it is not that bad. Okay, it decays by like a product in like, so epsilon becomes epsilon by log n in terms of size, and times a log n factor. Okay, is that theorem statement clear?
Yes, sir.
Okay, good. So one thing is, you can, there's a natural to ask is like, okay, so you're getting data over a stream. Okay, but you at initially you may not know the size of the number of points you will be getting, right? That's an extremely natural thing, right? I mean, if I don't know how many points I will be seeing over a stream, okay, then how will I like maintain corsets that whose size will depend on n and stuff like that? Okay, so this is a standard thing in streaming, which you can actually, there are tools like there are standard techniques to use, okay, where you can remove this, remove the condition that you know the size of the number of points or like number of points you will be getting over a stream. You don't have to know the number of points you will be getting beforehand. Okay, there's a techniques of doing this. I don't want to get into those now. For this theorem, I will assume that you know number of points you will be getting over a stream. Okay, so n is known. N is known to you. Okay. Again, as I said, this is a very standard thing in streaming. This doesn't have to be the case. You can work around it. Okay. But again, for simplicity of presentation, I'm assuming, okay, you know n. Okay. Then can you maintain? Okay. So how should we go about doing this? Okay. So the idea is like, okay, so I will be getting points P1, P2, Pn. Okay. I will be seeing one at a time. Okay. And in terms of calculating the Corset A epsilon, it may be the case that I may end up looking, I need to end up looking at all the points, right? Corset is like size of the Corset may be independent of the number of points, but the points that you choose to make your Corset will obviously depend on your input point set, right? So because it's a subset of the input point set. So without looking at all the points, how will I compute it? Okay. This is where these nice properties, the definition, again, I said, the definition is set up in such a way, okay, so that we can get around these bottlenecks. Okay. So what we do is basically, like in terms of symbolically, as if I have partitioned the point set into batches. Okay. Batch 1, batch 2. Okay. So some, let's say batch T. Okay. Okay. And let's say each batch Bi is of size small b. Okay. So T is something like n by b. Okay. So what your streaming algorithm, so what is the idea behind it? Your streaming algorithm will do is, first, when you get the first b points, it will store all the b points. Okay. Then compute the Corset of, so let's say, let's fix epsilon prime to be something like epsilon by log n. Okay. So it looks at the first batch B1, it store all the points in B1. Okay. Then looking at the B1, it computes a Corset 1 plus epsilon prime Corset. Okay. Then completely throws the set B1. Okay. Then look at B2, store the points of B2, again compute the Corset 1 plus epsilon prime Corset. Okay. And then combine this Corset over a tree. Okay. So what is the idea? So let me do it pictorially. So you have this batches B1, B2, BT. Okay. So first it will look, so first it will take, so it will compute the Corset for B1 and Corset for B2, and it will send it to this node. Okay. This node will do what? This node will compute 1 plus epsilon Corset for both the Corset C1 and C2. Similarly, again B3, B4. Okay, you will send the Corset for B3 before here, which is, let's say, C3, C4. At this node, you will compute the 1 plus epsilon Corset of C3 union C4. Again, combine. Here, let's say you get a Corset. So let's call this Corset, you get C12. Okay, C34. Okay. At this node, you will compute 1 plus epsilon prime Corset for C12 and C34. And this is the way you process to finally get the final Corset. Okay. Is the idea clear what we are doing? So let's say I'm doing it in the offline mode. Let's say all the points are given to you. Forget about the streaming. Let's say all the points are given to you. I want to have an inefficient Corset construction algorithm. Okay. And I'm doing this. I partition my point set into these T batches, and I will be processing these batches in this way so that I get a Corset. Does it make sense? This thing?
Yes,
This
sir.
algorithm? So finally, I will get another Corset here. Whatever B is guaranteed. Okay, some beta Corset I will be getting. Okay, whatever be that corset. Okay, but I will be getting a corset. Okay, and I want to show that beta will be 1 plus epsilon. Basically, the way we have fixed the parameters, it will become 1 plus epsilon. Okay. Okay, so if I do this, what will be the size of the tree?
Log n.
Yeah, log n. It should depends on the batch size, you know. Pardon? Come in. Someone was saying something. Can you come again, please? Hello? Am I connected or am I have to reconnect? Saket, can you hear me?
Yeah, we can hear you. Yeah.
Yeah,
We can hear you.
So yes, there was someone was asking a question. I just got. I did not get it. What you were saying something? So okay. So let me. Okay, so again, so let's forget about streaming for the time being. Even though there is an efficient way of computing Corset, I am now building. I want to design an inefficient way of computing this Corsets. Okay, so I partition the point set into batches, and I will do this tree processing to get a Corset. Okay. So finally, at this node, at the root, I will again get a Corset. Whatever be the guarantee, I will get a Corset. Okay. So now the question is, what will be the height of this tree?
So log of the number of batches.
Log of the number of batches, right? So basically plus like flow ceiling maybe. Okay. So log of n by b plus 1, something like this height, right? It's okay. And how many points am I storing at each of these internal nodes at most? A of epsilon by log n, right? Or let's say A of epsilon prime. Okay, so let's epsilon prime is our epsilon by log n. So A of epsilon prime is the number of points we store at each internal node. Let's say at each internal node. Okay, so if I take the union of the number of points I will be storing over all the internal nodes, it will be something like log of n by b plus 1 times A of epsilon prime. Right? This is okay? Okay, good. So, right. So now, let's see one thing. Okay, so can we figure out what will be this beta? Okay. So beta will be, it will be a beta corset at the root, right? But what will be the value of this beta? Okay, so before we do that, let's see what will be the value, what will be the quality of the corset at this node. This red thing that I'm circling, at this node, what will be the quality of corset with respect to the set B1 union B2? Okay, C1 was an alpha 1 plus epsilon prime corset for B1. C2 was 1 plus epsilon prime corset for B2. I took their union. Okay, B1, B2 are disjoint. So C1 union C2 is a 1 plus epsilon prime corset for B1 union B2. But C12 is 1 plus epsilon prime corset of C1 union C2. So C12 will be 1 plus epsilon prime square corset for B1 union B2. Is that clear? Basically, I am doing disjoint union and reduced property is what we are using here. Is this clear that C12 will be a 1 plus epsilon prime whole thing square corset for B1 union B2.
Yes, sir.
So now you can just like inductively prove that beta will basically be 1 plus epsilon prime to the power h corset for your whole point set P. Okay. At this node, you will be getting corset for B1 union B2 union B3 union B4. Right? C34 will be C34 will again be 1 plus epsilon prime square corset for B3 union B4. Again, that combine, take the product with 1 plus epsilon prime and keep going. Okay. Right. So, and now you just fix to find what should be the parameter B. Okay. You just solve. You solve for this 1 plus epsilon prime to the power h equals to 1 plus epsilon. Okay. And you need to check it, but as far as you remember, so B you have to take it. So the small b you have to take to be something like a of epsilon by log n. Okay. If you take small b to be something like this, it is good enough. Okay. Okay, good. So this is we got like a really inefficient algorithm. Okay, we have now a 1 plus epsilon corset of size. What is the size? A of epsilon by log n times log n. Something like this. Okay, good. But even though this is like a worse way of computing the corset, right? We already have a better corset bound, right? A of epsilon. Okay, but this algorithm you can implement over a stream. That's the interesting thing. Okay, so the idea is you will maintain this tree symbolically. Okay, first over the stream you will be getting the set B1. Okay, whenever you get the set B1, you calculate the corset C1 and send it to this node. Okay, then you will get the set B2. Okay, once I have calculated C1, I will throw away all the points in B1. Okay, I will only maintain the subset C1. Similarly, when I get the again like get all the points in B2. Okay, when I get all the points in B2, I will again compute C2, send it to this node and throw away the rest of the points of B2. So for this node, since I have got C1 and C2, I will instantly calculate the corset C12 and I will maintain it like this over the stream. Okay, so over the stream, if I implement like this, what will be the space complexity of the algorithm? See, the space complexity of algorithm will be the number of points you store at each internal node of the tree plus the size of the batch that you are keeping for the time being to compute the new corset. Okay, so it will be basically B plus A of epsilon by log n times log n. Okay, which is the way we have selected B, it turns out to be, which is order A of epsilon by log n times log n. Okay, so this is basically the sketch of the proof. Okay, is the idea behind the proof clear?
Yeah, sir. Yeah.
Right. See, the corset for so to compute a corset of size A epsilon, I am doing it for a generic function, right? I don't know how what you have to do on the input point set to get a corset of size A epsilon, right? It may be the case you need to like do a lot of computation on all the input points. Okay, I cannot throw away anything from the input points. Okay, so that is not something I can implement over the stream. Then I will be storing all the points in all the points that I get over the stream and then compute A epsilon. This gives me a scheme. So, okay, I getting a slightly suboptimal, not much, but like in terms of log factor, slightly suboptimal size corset, but I'm preserving the guarantee 1 plus epsilon. Okay, so this is what disjointness property gives you. Okay, and this is a very generic result, by the way. This is extremely generic result. Okay, nothing to do with how you calculate that corset A epsilon. Nothing to do with it. Okay. Any cost function for which these properties hold, you will be able to calculate a coset over a stream with this complexity. Okay, good. So we have I've already told you that for minimum enclosing ball, so like let's say look at again that example. So for minimum enclosing ball, okay, we know that there exists a coset of size 1 by epsilon to the power d minus 1 by 2. Okay. So for points, if you get points over a stream and I want to keep the coset for C of MEB, okay, what will be the size of the coset then? So over a stream, I will be able to maintain a 1 plus epsilon size, 1 plus epsilon coset, 1 plus epsilon coset for C MEB of size MEB of size order log n to the power d plus 1 by 2 by epsilon to the power d minus 1 by 2. Okay, this one log term is more because of the log factor we have in the theorem. Okay, good. So this is fine. So this is even without knowing how you construct a coset of size 1 square root epsilon to the power d minus 1 for a C of MEB. Okay, that I don't even know how to do it, but just that is there, then this result will directly follow from this theorem too. Good. So now we will be showing you a construction of coset where actually this won't be required. I will be storing only these many points. That itself will be good enough. Okay. So Saket, how much time do I have?
For the first lecture,
Yes.
it's okay. Take your time, like no hurry.
Yeah,
Go
we
at your
started like
pace.
5 minutes. Oh, okay.
Yeah, go at your pace. It's perfectly
Oh,
fine.
okay. Good. So now we will see how to get a coset for minimum enclosing ball. Okay, so this is really it's a very simple idea that actually came from like a result in convex geometry. Okay, and people in CG just basically adapted that technique here. That's it. Okay, so before I give you the technique, so let me tell you a very interesting result from convex geometry. Okay, so the result, let me tell you the result first. Okay, so so this is the result is due to Dudley. Okay, and then Bronstein also, but so there are two variants of it, but like let me give you the Dudley's result. Okay, so this is approximating convex bodies. Convex bodies. Okay, so the idea was the following. Okay, let's say I have a convex body. Okay, that is contained inside a ball of a convex body in RD. Okay, C. So I should not use C. Let me write like this. Okay, it's a convex body in RD that is contained in a ball of radius 1. Okay, and what I want to do is, so this convex body may have like lot of like it may not be like very hard to store. Okay, I mean ideally we want to store discretized version of these objects, right? Okay, but I want to store a convex body which is like a discretized version of this C, a convex body C hat, okay, which is a polytope. Okay, but it should have some good guarantees with respect to C. That is what the goal is. Okay, so what I do is the following. Okay, I take some set of points on this unit sphere. Okay, okay, in such a way that take any arbitrary vector v, unit vector v. Okay, there will exist a vector that I can get with these red points such that angle between any vector u, there will exist a red vector whose angle will be at most, let's say, square root epsilon. Okay, so I have taken enough number of points on the unit sphere in such a way that take any vector unit vector, I will find a red vector. So what is a red vector? Red vector is the one I get by connecting the center with a red point. Okay, I will get a red vector whose angle between that your vector will be at most square root epsilon. And this is true for all, like doesn't matter which vector you choose. I will always find a vector that will be a close approximation. Close means the angle between the vector you have chosen and the red vector that I will give you will be at most square root epsilon. Okay, is it clear how what are the properties of these red points? Okay, so now what I do is I just project these red points orthogonally on the convex body. Okay, I just do it, okay, like this. I don't know why I'm drawing all of them, but anyway, since I'm doing it, so let me do it. I get this green points, right? I project all the red points that I have on the sphere on this convex, on this way. So I get a set of red green points. S is the set of green points we got. So let me not use the green way, by projecting the red points. The red points on C. And now what I do is I just take the convex hull of these green points. Okay, convex hull is does everyone know what is the definition of a convex hull? So convex hull of a set of points is basically the smallest convex body that contains that point set. Okay, so convex hull of S will be a C hat. Okay, the nice thing about this C hat is, so this is like basically a discretized approximation of the convex body C. Okay, what guarantees does it have? The guarantee it has is the distance between so I don't want to get into the exact definition. It is an epsilon approximation of C. C hat is an epsilon approximation of C. Okay, so then one natural question that you can say is, okay, what are you doing? I can take all the points on the sphere, project it on the convex body. I will get the convex body itself when I take the convex also. What am I doing? You're not doing anything interesting. The thing is that the number of points you need to, like number of red points that I need to do this will be basically 1 by square root epsilon to the power d minus 1. That's it, not more than that. And number of points I'm selecting here is independent of the convex body. It doesn't matter what the convex body is. The number of red points I will be selecting on the sphere will be exactly this. So whatever be how complicated the convex body is, I don't care. Okay, the number of points I will be using it to get a good approximation of it will be exactly 1 by square root epsilon to the power d minus. Okay, obviously there is a term that depends on d, okay, constant, but forget about that for the time being. Okay, so this was basically Dudley's result, which is like a really beautiful thing in convex geometry. This is basically what they used. Okay, what we will be using, this idea of this construction is what we will be using to get a 1 plus epsilon corset for of size whatever we mentioned now. Okay, so let me do it now. So is the intuition clear? Okay, so let me write the theorem for CMEB. We will show existence of 1 plus epsilon corset of size order to the power d minus 1. Okay, good. Okay, so before I prove this, I will be using one simple thing, what is called theta net on a sphere. Okay, so theta net on a sphere is exactly the thing that I used. So the red points that I took for approximating the convex body was basically a square root epsilon net on the sphere. Okay, so what is a theta net on the sphere? Okay, so let me write the definition. For theta greater than 0, we call the vectors v equal to theta net if for all vectors v in Rd there exists a vi in v. So let me write v like this, vi in v, such that angle between v and vi is at most theta. Okay, so this is what we call theta net. Okay, and these vectors, like these vectors that we are taking v1 to vt, will be unit vectors. Okay, take them to be unit vectors. Okay, is the definition clear for theta nets? Okay, so just it's a simple thing to prove is that there exists a 1 by f theta to the power d minus 1 size theta net in Rd. Okay, why is this the case? So I mean, I'm giving you the intuitive proof, but this proof has all the ideas. So let's say I want to do it for circle. Okay, so for circle, how many points basically I need is 1 by epsilon, and that we can see very easily, right? What we do is we just partition the boundary of the circle into arc of length theta, right? And how many partitions will I have? Basically 2 pi by theta many, right? Okay, and the vectors I will be taking are these vectors, these middle things, or maybe I say the arc length I can take to be 2 theta. Sorry, so 2 theta. So the size will be like pi by theta. Okay. Okay. I mean, you just have to generalize it for higher dimension, you will get the bound. Okay, so there's nothing fancy happening here. Okay, so let's see. So how do we prove the existence of 1 by epsilon to the power d minus 1 by 2 net? Okay, so first we do is, so let's see the proof of the theorem 1 that we promised. Okay, so what I do is I first take theta net v1 to vt, okay, is a square root epsilon net. Okay, good. So now how do I compute the corsets for P? So the set of point is, let P be the set of points. P is the set of points for which I want to compute the corset. Okay, so how will I compute the corset now? Okay, so the idea is I will build a set S, which is equal to S. It will be equal to union over all Vi belonging to V. Okay. Sorry. Argmax of Vi comma Y y belonging to P, comma, argmin, y belonging to P, A, comma, y. So this set will be our epsilon 1 plus epsilon corset for P. This will be a candidate. So what am I doing basically? I have this epsilon net for each vector V in my square root epsilon net. I will look at those points. I will keep 2 points for each vector V from my point set P. One that has the maximum dot product with respect to Vi, and one that has the minimum dot product with. So this is basically the dot product. As I said. Dot product with respect to Vi. This is notation. This is a dot product notation. Okay. One that has the maximum dot product, one that will have the minimum dot product. Okay. And I will do it for all Vi. That's it. Okay. So each vector Vi in V will give me, oops, I'm sorry. So let me just connect this. Each vector Vi in V will give me 2 points. Okay, from P. Okay. I know the size of T is from that theta net thing, that T is 1 by, just 1 second, what happened? Just 1 second. This is a problem.
I think your pen had very small number of small battery.
Battery, I don't know what is happening. Okay. So let me talk, and then we go for a break and then come back and finish the proof. So for each point Vi, okay, I will get 2 points from P. Okay. And what is the size of Vi? T. T is at most square root 1 by square root epsilon to the power d minus 1. Okay. So Saket, let's take a 15 minutes break. Then I'll start at 4 and I will finish this proof and give the other one. Okay.
Sure.
And I charge my pencil or get a pencil from sort of. Okay.
Okay.
So,
sure.
And we will show that S is a 1 plus epsilon. Okay.
Okay, people. So let's have 20 minutes break and let's convene at 4 o'clock.
Yes, convene at 4 o'clock.
Okay.
So I am just, what should I just stop the broadcast?
It's up to you. I mean, you can just leave it here. It's perfectly fine.
Okay. But let me stop the mic then.
Okay.
Microphone.
Sure.
Yeah. Okay. Okay then.
Okay. See you at 4.